equation, and then it has the solution as Tx is equal to F1 T plus Cx plus F2 T minus Cx.
What is F1 and F2?
F2?
What is
F1 and
F-
F2?
Yeah.
These are arbitrary functions.
Arbitrary functions.
And
So if you have initial conditions for B and its derivative, say at 0, then you can determine F1 and F2.
that's what he did right after
Okay.
this. And then, well, this is this solution in the Lumber's way, and then he says if the initial condition in the form as V0 x is equal to Gx and Vt0 x is equal to Hx, so this is the mixed type of boundary condition. And the solution, this solution, in order to this solution to satisfy the equation with this initial
Excuse me,
condition.
let me do one. Well, that's wrong. Anybody notice what's wrong with that solution? Yeah, well, if it says C squared, then that's correct. Yeah.
Yes.
By the way, do you know how to get this, that this is the arbitrary solution? You basically factorize that operator. Let me show this, it's very simple. I mean, this equation is dt squared minus c squared dx squared. That's the wave operator, making it be equal to 0, right? So this operator, well, it's a difference of squares, so this operator can be written as dt minus c dx dt plus c dx, right? And so, well, you just multiply it and you'll see that it's equal to that. And now you see that this, this is first order. And any function that of this type, this acting on that will give you 0. And this acting on that will give you 0. And therefore, I mean, this guy acting on any of this will give you 0. So that gives you an arbitrary solution.
And I believe that the equation in this time, this form can also be solved by eigenfunction.
Yeah, but then it's much more difficult. It depends on the boundary conditions. And it's basically a Fourier transform. You would need a Fourier transform. Or Fourier series if there is an endpoint. And you'll get to do Fourier series.
And he said, with this initial condition, this type of solution, in order to satisfy this equation, F1 x plus F2 x should be Gx, and C F1 prime x plus C F2 prime x should be Hx.
Is that clear how to get this? Well, you just substitute t equals 0 there, and then you take the derivative, and you'll get extra c there.
And then from these two conditions, we can specify what F1 and F2 looks like.
How do you solve for F1 and F2 from
Take the
this?
derivative of this one.
Okay, and then solve linear system, yeah.
He says F1x should be f Gx plus 1 over
Yeah, you could erase that.
2c 0 to x, which is the first part,
And so if you then substitute over there, you'll get the solution. Is that clear how you get F1 and F2? As you mentioned, you just well, you could integrate the second equation from 0 to x, and that's where those integrals come from. Then you will get linear system, divide by c, and integrate it over x, and so, and then you just solve them, and that's what you get.
And then he went on to.
Oh, there must be minus on the second equation.
Right here?
Yeah,
Yeah.
because otherwise, yeah.
Oh, yeah. And then he went on to talk about the higher dimensional case, and I think it's more rigorous and complicated. And I think I'm not really comfortable talking about that, so if somebody's willing to talk about it the next time.
Well, can you mention some equations that he writes, at least in this high-dimensional case? With Laplacian, with elasticity equation, just write them down. How does it look in higher dimensions?
Well, in higher dimensions.
But let's write the equations down, yeah.
It covered the same, exactly the same basic idea to derive the equation, but at the end, what he got for the
There is more space, so that is more space.
tt minus I'll just say 2a equal to 0. So the thing that we have to notice that for
What
higher
is
dimension.
xx? Well, if you write xx, then you don't need Laplacian or vice versa. Don't write xx then.
The thing that we have to notice for the higher dimensional case is that instead of omega xx in the previous case, there is the Laplacian there because it's higher dimensional, and I think that's the only difference in the standard form.
Well, for linear, yes. For
Yes.
linear equation.
Yes.
But then you get some other, like elasticity equation.
I didn't really get into that.
Oh,
So
can you just write it down? Okay, let me, well, I guess, yeah, you finished, right? So there is just 5 minutes. Let me just give you the idea how you do high-dimensional case and what it actually means. So what does vibrate? So you talk, well, what he was describing is basically U was this map for fixed t. T is always a parameter, so just don't look at t. So it was, well, it was an interval to RK. It's basically the vibrating of these maps, right? So you embed this, it's somehow embedded in, and you could fix some 2 points, not necessarily on one line, just pick. It's a one-dimensional thing sitting in RK. And so if it depends on time, you could turn on your movie and it will start vibrating, right? Fix that. So now, well, instead of this being one-dimensional interval, consider this to be, well, let me change notation, let me call it omega, where this is not one-dimensional, but sits, say, in n-dimensional space. It could be a manifold or submanifold, such that this is, if you want, you could look at it as a surface of a submanifold sitting in RK. Okay? So, n is less or equal than k. So, for example, a surface. If it is a membrane, then it's called, well, you would have, instead of this string with fixed end that kind of wiggles in RK, you would have now, well, and you could fix some boundary condition, and then it will vibrate. It's a membrane. Okay, and so if this is N, then sometimes it's called, well, if this is D, then this is called D brane. You may have heard that word, and kind of buzzword, D branes. Well, it comes from membrane. Membrane for D equals 2. So 3 brane would be vibrating 3-dimensional submanifold. In other words, kind of 3-dimensional surface, if you want. Okay, and so in general, it is N. Okay, I don't like the word D brane, so it's just N. So you have that map, right? And the rest is pretty much the same. You write your action. So this is T1 to T2, and then an integral. So it's the kinetic energy. Well, the kinetic energy is always dt of this u and then square. Well, you could put mass if you want. So there is dx, and now you're integrating over that. So this guy u, of course, what is that u? Well, u depends on t. It is a vector in our k. It's still a vector in our k, in that k-dimensional space. It depends on t, and it depends on x1 and like n variables now, right? So before it was only one variable x. Now there are n. So and this is a vector itself. So these are completely different vectors. This is a vector in k-dimensional space. This is a vector in n-dimensional space, right? So I'm going to introduce two different kinds of indices. Like this, I will call it u mu, where u goes from 1 to k. Well, let's call it I. In other words, like an indices always will run from 1 to k. And for x, I'm going to write x mu, and u will always run from 1 to n, whatever I have. So then there is no confusion. Greek means from 1 to k in a bulk space, and mu means the coordinates on that brane. Make sense? Okay. Then, well, of course, here this is an integral in this n-dimensional space. Well, this could be a scalar, and of course you could do more general than that, but that's fine. What is this? Well, that's dt ui, and then, well, in general you'll get a metric here, but for that there is no metric, so you just dt ui, and that is sum of I. That's what this is. That's kinetic energy, right? It's still the same. It's a vector in our case. And then there is minus the potential energy, right? And so what is the potential energy? Well, if you just throw it's some function of the gradient. Well, we could still say that it is a function of the gradient, but now gradient of this function with respect to these coordinates. So it's some function, I'll call it f. That depends on, well, let me call it this way. What is this guy? Well, this is dui by dx mu. So let me call it y I mu. It is two indices, right? So if you want, it's a rectangular matrix where I goes from 1 to k and mu goes from 1 to n. Is that clear? So, well, sometimes these are called fields. I mean, this is basically a field in it's a vector valued field in n-dimensional space. Okay, it takes you can represent that u as u1 of x, like uk of x. So it is a vector where x is an n-dimensional coordinate. Okay, is that clear? And of course, everything depends on t. So, and if you do this, then what you want to derive, and you have some boundary. Well, this guy has some boundary. Let's see. If this is n-dimensional, then this is n minus 1 dimensional. Okay? And then you need to impose boundary conditions. Well, let's say